Welcome all of you. In the last 2 or 3 classes, we discussed extensively about chemical shifts, one of the internal interaction parameters within the molecule, and we discussed how the chemical shift arises, what are the parameters or factors which govern the chemical shift, and chemical shift what happen, how do we see that when there is a symmetry in the molecule, or when there is a chemical equivalence of different protons in the molecule. And we also understood how do we express chemical shift in ppm, and with a reference measure the frequency of the signal with respect to the reference and divide by the resonating frequency. We know we can express the chemical shift in ppm. That is what we understood. And I said chemical shift in expressed in ppm, it removes field dependency. There is no field dependency. And for different nuclei to express chemical shift or to determine measure the frequency, we have different references. For proton, carbon, silicon, I said tetramethyl can be used. For different nuclei, we have different references. How I also discussed extensively how do we convert ppm to frequency and frequency to ppm for different nuclei in the same spectrometer or in different spectrometer. How do you convert it? And I also showed that there is a field dependency for the chemical shift, especially when expressed in frequency. You can see that there is a better dispersion. Better dispersion causes better resolution. You get better resolution as you go to higher and higher frequency spectrometer. The peaks start moving far away. The dispersion becomes much better. Very easy to analyze. You get better resolution. And we discussed at stretch about factors governing chemical shift, like effect of electronegative atom, mesomeric effect coming because of electron donating group or electron withdrawing group, both in aliphatics and in phenyl groups. How in the delocalization of aromatics, what is going when there is electron donating group or electron withdrawing group, what will happen? How ortho and para positions are selectively affected and the meta position is less affected compared to these two. This is the case for, let us say, for electron donating group. If it is present, in case it gets reversed when you have electron withdrawing group. Similarly, what will happen to the magnetic anisotropy? What if you have a C double bond, C bond, C single bond, C triple bond, C necessarily group? What happened to the protons if it is situated within the cone of the charge distribution curves? What happens if it is situated outside, whether shielded or de-shielded, which depends upon whether it is a single bond, double bond or a triple bond which is present. So extensively we discussed all those things. We can keep on discussing about it for hours and hours, but at the moment I have given you the basic idea about chemical shifts. With this idea, we will go ahead and try to understand another internal interaction parameter called scalar coupling. If you understand these two, by and large you can interpret any NMR spectrum, especially the chemical shift and also the multiplicity pattern, that is important. So we will understand another important factor which governs the NMR spectrum, that is called scalar coupling, another internal interaction parameter called scalar coupling. This is called spin-spin coupling, also called indirect coupling. It is again, as I told you, it is a magnetic interaction. It is because of the two nuclear spins, there is an interaction between these two, where the magnetization or the polarization is transmitted between one nuclear spin to another nuclear spin, mediated through chemical bond, covalent bond. If there is a covalent bond, then what happens? This nucleus can give its polarization to this nuclear spin, and there is an interaction between these two. When these two are interacting, some effect is seen. What is going to happen for the NMR spectrum? What is that effect? That is what we will discuss today in spin-spin coupling. Before we discuss spin-spin coupling, scalar coupling at stretch, lot of things we can discuss. Before that, I will summarize some salient points of scalar couplings. What are the scalar coupling salient points? First of all, I told you it is a covalent bond mediated interaction. there must be a chemical bond for one nuclear spin to interact with another nuclear spin for J coupling to occur. For example, in a molecule like this interaction is allowed. This proton can give its energy to this carbon, polarization this carbon to this carbon and to this proton. The polarization transfer takes place through chemical bonds, that is allowed, whereas direct polarization transfer from this proton to this proton through space is not allowed. This is one of the salient features of scalar coupling. It is a covalent bond mediated interaction, and again this is also not allowed through space. Second, also this coupling is always denoted by Nij, is a term we use. Like chemical shift is always refers to as delta ppm. I said chemical shift is refers as a ppm scale, is also called delta scale. Coupling is referred to as Njij. N is the number of bonds, consecutive bonds separating the two interacting spins. For example, this proton and this proton are interacting, they are separated by 1 and 2 and 3 bonds. So this is called 3Jij between this proton and this proton. So Nij, N is the number of bonds, consecutive bonds separating the two interacting spins. J coupling also depends on the electron charge density at the site of the nucleus and are not averaged in the solution state. It depends upon the charge at the site of the nucleus, but they are not averaged out like dipolar coupling, which I said earlier. That means it does not depend upon the orientation of the internuclear vector. That is why it is called a scalar coupling. J coupling is called scalar because it does not depend upon the orientation of the internuclear vector. Third important point is the strength of this interaction. The interaction strength is few hertz to few tens of hertz. For example, the J coupling, if I said it could be 10 hertz, 5 hertz, or it could be 1000 hertz, 500 hertz, depending upon nuclei of interest or depending upon the interacting spin, two spins which are interacting, whether it is homonuclear or heteronuclear. So these are all, the strength can vary from few hertz to few tens of hertz, sometimes hundreds of hertz. The coupling interactions between two spins can extend beyond 1 bond, 2 bond or 3 chemical bonds. For example, there can be this proton to this proton interaction, it is 2 bond coupling. This to this is possible, 3 bond coupling. This is 4 bond coupling, 4JHH. This is 5JHH, 5 bond coupling. This is 6JHH, 6 bond coupling. So the value of the coupling, of course it can extend to several bonds, but remember the value of the coupling can be positive, negative or 0. The J coupling can be even 0 or it can be some value plus 5 hertz or it can be minus 5 hertz, possible. It has a value which can be either positive, negative or 0. Coupling can be between homonuclear and heteronuclear NMR active multiple spins. For example, if I consider a molecule like this, there can be 2 bond coupling between this proton to this proton. There can be 1 bond coupling between this phosphorus and fluorine. It is possible. This is possible and this is also possible. 2 types of interactions are possible here. This, if this proton and this proton, the coupling is there through bond, it is a homonuclear coupling. Proton and phosphorus coupling is a heteronuclear coupling, that is also possible. Consider a molecule like this. Now we have meta disubstituted benzene, fluorine and fluorine, there is a symmetry here. Okay, do not worry about more details about symmetry and everything, just for the sake of understanding I am telling you. There can be a coupling between this proton to this proton, 3 bond coupling, the homonuclear proton proton coupling. There can be coupling between proton and fluorine, again 3 bond, heteronuclear coupling. There can be coupling between this carbon and this proton, 2 bond coupling, heteronuclear. This is 1 bond coupling CC, homonuclear, 2 bond coupling carbon and fluorine, heteronuclear, and 4 bond coupling between fluorine and fluorine, homonuclear, 3 bond coupling between fluorine and proton, again heteronuclear. So many possibilities we can think of in a given molecule. There could be n number of homonuclear couplings, then can be n number of heteronuclear couplings possible. So any coupling can be between both homonuclear spins and also heteronuclear spins. And coupling constant is a scalar quantity. It is always expressed in hertz. It is just a number. If I say 10 hertz, just number. So, I coupling constant 10 means 10 hertz, that is all. It is a scalar quantity. It is always expressed as Jij. Another important factor is the magnitude of the spin-spin coupling, the strength of the coupling, scalar coupling is larger for one bond coupling. If the internuclear, if the two spins are separated only one chemical bond, the strength is more. If it is separated by two consecutive bonds, strength is much less. If it is 3 bonds, consecutive bonds separated by 3 bonds, even less. 4 bonds, it is less. It is just a order in which the coupling strength decreases. But there can be violations. It is only not that this should always be like this formula. It need not obey. It is generally the case, but there is a possibility that 2 bond coupling can be larger than 3 bond also. I mean 3 bond can be larger than 2 bond also. This is possible. But this is the general trend. So, as the number of consecutive bonds increases, the strength of the interaction keeps coming down. The coupling constants are independent of the magnetic field. Remember, I told you chemical shift has a field dependence. As you keep on increasing the magnetic field, I said there is a more and more dispersion is there. Peaks have started moving away. There is a field dependency for chemical shift. But for the scalar coupling, there is no field dependency. It is independent of the applied magnetic field. Coupling constants, whatever the value you measure in a particular frequency of the spectrometer, go to any other spectrometer to any other frequency, the coupling constant remains same. It will not depend upon the magnetic field. And the splitting patterns is independent of the sign of the coupling constants. We will discuss that later. For example, I have a doublet here. I measure this coupling, some value. Doublet comes because of splitting, because of J coupling. Some value, let us say 10 hertz. I make it minus 10 hertz. This pattern remains same, it will not change. You will not be able to find out by looking at the spectrum whether it is positive or negative. The splitting patterns are independent of the signs of the coupling constant. And one spin can simultaneously experience coupling with several other chemically inequivalent spins with different strengths. For example, look at this molecule. Then I will consider this proton. This proton can have molecule is a simple molecule, one single molecule, very simple molecule. But this proton can have a coupling, scalar coupling with lot of other nuclei. For example, it can have one bond coupling between carbon and proton. This proton can interact with this carbon, one bond, J coupling is possible. 2 bond, this proton can couple to this carbon, that is also possible. This proton can couple to this fluorine, heteronuclear 3 bond coupling is possible. It can have a 4 bond coupling with this carbon, heteronuclear coupling. It can have 4 bond coupling with this phosphorus, heteronuclear coupling. It can have 5 bond coupling with this carbon, heteronuclear. It can have 5 bond coupling with this fluorine, heteronuclear again, and it can have 3 bond coupling with homonuclear proton-proton. It can have 3 bond coupling between this carbon and this proton and this carbon, that is also possible. You can have 4 bond coupling with this proton and this proton. See, one proton, one hydrogen in this molecule can have 10 different couplings. It can experience coupling, it can couple to any of these nuclear spins, and the strength of the interactions will be different, it need not be same. This one bond carbon coupling may be 150 hertz or 200 hertz, this can be 10 hertz, this can be 50 hertz, like that. Different interaction strengths are there, but one spin can simultaneously interact with all other spins. This has 10 couplings. Similarly, if you look at this proton, it can work out. You can find out this can have 1 bond coupling here, 2 bond, 3 bond coupling with this, 2 bond, 3 bond coupling with this, 3 bond coupling with this proton, like that you can work out. This can also have 10 different couplings. So, each spin in a given molecule can have n possible interactions, n types of interactions with different nuclear spins, with the strengths being different also, it need not be same. Of course, so far I was telling you we get the J coupling only mediated through covalent bond, but in some rare examples like a molecule like this, you can get coupling between this fluorine and this CH3 proton and this fluorine not mediated through covalent but directly through space. Similarly, here through space coupling of 8 substantially large value you can see. In these cases this coupling is not covalent bond mediated, it is because there is it so happens the lone pair electrons of these two nuclei are within van der Waals contact. There is a direct transfer of polarization between these two spins. As a consequence we can see the interaction, but not through covalent bond, through direct. These are all rare examples, not always, but all the time majority of the cases are 99.9999% of the cases, except one or two rare examples like this. The scalar coupling is an interaction where the polarization is transferred through covalent bonds. That is the important thing. And one particular peak can split into multiplicity of peaks due to coupling interactions. I told you in the one previous molecule which I showed in the benzene ring, one proton can have 10 different couplings. What happens when the protons are coupled to other one proton is coupled to several other protons or several other carbon, fluorine, phosphorus. When it interacts with other nuclear spin, then this peak will divide into 2. 1 will become 2, 2 will become 4, 4 will become 8, like that. There is a multiplicity. Because of interaction there is splitting of the energy levels. As a consequence, particular proton or particular nuclei which you are observing can give rise to multiplicity pattern. So, one peak for example, it will be a single peak without any coupling. If it is coupled to another proton, it can become a doublet. If it coupled to another proton, doublet of doublet. Coupled to another one, it will become doublet of 4 line pattern. Okay. But remember, this, let us say intensity is 100. When it divides into 2, it will become 50-50. When it divides further into 4, it will become 25-25. When it divides further, it is 125, 12.5, 12.5, like that it goes. You add up all these intensities, 12.5 into 8, it will become 100. So, this is the intensity. So, the total intensity of a particular peak will remain same if you measure the intensity of the entire multiplicity. That shows the number of, I told you the proton count, the peak integral area gives you the proton count. If this total area corresponds to 1 proton, then all the multiplicity area, if you consider, if it is a CH proton, let us say 1 C proton which is divided into 8 peaks because of coupling with 3 other protons, but the total integral area is same as this one. So, the multiplicity will be there, but the total integral area of the uncoupled peak, uncoupled proton and the multiplicity coming because of coupling with other proton remains same. Remember, the total integral intensity of the uncoupled proton and the multiplicity pattern coming because of coupling with several other protons, the total area remains same. That is why we can get the proton count if we get the integral area. Is it clear? Now let us go to the next one. The multiplicity of the peaks due to coupling with chemically equivalent spins is always given by a formula called 2Ni plus 1, especially in the weakly coupled case. I will tell you what is weakly coupled and strongly coupled when you go ahead. But remember, there is a multiplicity and that multiplicity can be understood by this formula. And for coupling among equivalent spins, we can also get the relative intensity of the multiplicity. Here we said for chemically equivalent spins there is multiplicity because of 2Na plus 1, and each line if I measure get it, and I can measure the intensity of each of these peak, that is given by what is called a Pascal triangle or a coefficient of binomial expansion. When we go ahead further we will discuss that. I will show you, I explain everything in detail. So, these are some of the salient points of scalar couplings. Okay. Before we go further, we should know what are the factors. The scalar coupling is a very simple, a very small interaction, especially when it is when we are dealing with protons. But So many things, information is available. These are all the features, salient points which you should remember when you want to understand scalar coupling. Okay. Now as I told you, when these two nuclear spins are interacting, when there is a scalar coupling, I said there is a multiplicity coming. Because of splitting, I showed you in the previous slide, 1 will become 2, 2 will become 4, 4 will become 8. How that peaks are coming? How so many peaks came? How 1 became 2, 2 became 4? This is because the energy levels of the particular spin get split when it interacts with another proton or another spin. When the energy levels are split, the number of transitions become more. As a consequence, we get multiplicity. We will understand taking example of two protons which are coupled between themselves. The J interaction always results in splitting of the energy levels. J result. J interaction results in splitting. And how the splitting takes place, how many splittings are there, how many one energy state will become 2, 4 or 8 depends upon number of spin states of the coupled spins. If one is coupled to other proton may have 2 spin states because of alpha and beta. If it is coupled to 2 protons, then there are 4 possible spin states, alpha, 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 beta, beta, alpha, beta, beta. If it is coupled to 3, then you have 8 possible spin states. I remember I explained to you earlier. The number of possible spin states goes by 2 to the power of n. We will understand that now more in detail. Then each spin will give rise to multiplicity pattern at the respective chemical shift position based on how many number of spins to which it is coupled to, how it is interacting. That will decide about the multiplicity pattern. Now I will consider for a single spin, what are the possible orientations we discussed. I told you if I have only one proton for a CHCl3, I took the example in earlier case, one proton, isolated proton, do not worry about the coupling with other things, it has only 2 spin states because this proton can have alpha state, spin up state, beta state, spin down states. So there is no interaction, there are only 2 energy states, the transition between these two is allowed according to the selection rule which I discussed. So you will get one peak. So single spin without coupling to any other thing, isolated spin always gives a single peak. That is why I said CaCl3 gives a single peak. Fine. What happens if there are 2 spins? How many possible energy states are there when there are 2 spins, especially when they are coupled, when there is an interaction between them? Spin 1 can have alpha and beta orientation, spin 2 can have alpha and beta orientation. Now we can think of the possible orientations, combinations of that. Before that, let us see how it is splitting. Now we will consider proton 1 and 2, I call it as A and X, spin A and spin X. Let us consider proton X. There are only 2 protons we are considering, each of them has alpha beta, 2 orientation. Let us say this is for A, this is for X. Now I am considering proton X. This proton X can see proton A either in this state or in this state. There are 2 different energy states. So proton X can see proton in the spin up state or in the other state which is spin down state. Okay, that is alpha state and beta state. There are 2 possible orientations. When it is, let us say this is a spin down state, this is a spin up state. Now what will happen with respect to this original position before interacting with the proton A? This will be the position of, let us say, proton X. Because it sees this in the alpha state, this is moved by certain value, because it is seeing the proton A in a which is in alpha state. There is energy difference, there is small change in the energy. Similarly, this proton X can also see proton A in beta state, it moves towards the right side. Alpha and beta, where one has a higher energy state, other lower energy state. As a consequence, this proton X can see this proton A with some value which is more, some value which is less. As a consequence, it moves the peaks in two different positions, one to the low field, one to the high field region. You understand? The proton X sees proton A in two possible orientations alpha and beta, and it splits this into two, and because of splitting of the energy level, one moves to the down field, one peak moves to the high field. So, proton X will become two lines. It splits into a doublet because of interaction with proton A. Fine. Now, what about proton A? We looked at proton X. Look at proton A. Proton A again sees proton X as in the alpha state, proton X in the beta state. Again it moves, it will split into two, one moves to the low frequency, one moves to the high frequency region. Essentially what is happening is, when two protons are interacting, each proton will see other proton in alpha and beta spin states. As a consequence, it will become a doublet. So, basically when you have two protons which are coupled, I call it as a weakly coupled, we will see what is weak and strongly coupled later. Then at the chemical shift of position of nu A, without any splitting, it will be a single peak. At the nu X, if there is no coupling, it will be a single peak, but because of the coupling, it will become a doublet. From the center, it moves by certain amount here, from the center, it moves by certain amount to the left. So, this moving to the high field and the low field by equal amount, and if I measure the separation between this and this, that is called interaction strength, J coupling. It is a scalar coupling, and this proton X is becoming a proton A is becoming a doublet because of X, and if I measure the doublet separation, that gives me J coupling between A and X. This is called JAX. Similarly, if I take proton X will become a doublet because of proton A. Measure the separation, this is JAX, exactly same, identical. So, when two protons are coupled, each proton will be a doublet. Remember, each proton will be a doublet, and the separation of this doublet gives you J coupling value. That is what you are going to measure, and the center of this doublet always correspond to its chemical shift. Center of this doublet correspond to chemical shift of X, center of this doublet correspond to chemical shift of A. The separation between these two doublets correspond to J coupling. You understand? So, one important point which you should know here is, proton A sees proton X in two spin states alpha and beta, and its energy is split into two. Proton X sees proton A in two spin states and its energy is split into two. So, alpha state has lower energy and beta state has higher energy. So, as a consequence, each peak is split into two lines. Please remember this statement. When two protons are interacting, each proton is split into doublet because of its interaction with the other proton. And interesting thing what I wanted to tell you here is, please note, when A was coupled to X, became a doublet, X is coupled to A, became a doublet. It means the interactions in NMR are always mutual. If A is a doublet because of X, X is also a doublet because of A. So, interactions are mutual. As a consequence, you got doublets in both of them. So, if you measure the doublet separation for each of them, that gives you coupling interaction between A and X. Center of each doublet gives you respective chemical shifts. This is what is important to understand about the interaction, how the multiplicity comes when two are interacting. What happens if three protons are coupled? You can work out the same way. It is not difficult at all. But remember, when one proton is there, if this is seeing other two protons, each proton will have alpha and beta state. Now, various combinations we can think of. This can see this in both up, down, up, both down, down, one up, one down, and this down, this up. See, each proton will see other three protons in four possible spin states. Then what will happen? 1 will become 2, here 1 became 2 because of 2 states. Now there are 4 possible orientations, it will become 4 line pattern. If it is coupled to 3 protons, then you have 8 possible spin states, then it will become 8 lines. That is how the splitting keeps going. Remember, the splitting of the energy levels, a particular proton splits into n number of energy layer states depending upon spin states of the protons which it is coupled to. If one is coupled to other proton, there are only 2 possible spin states, alpha and beta. If one proton is coupled to 2 other protons, there are 4 possible spin states, it will become 4 lines. If one proton is coupled to 3 other protons, there are 8 possible spin states, it will become 8 lines. Like that multiplicity comes. So more about the multiplicity of the coupled spins we will discuss later. Today I am going to stop here because time is getting over. Please remember what we discussed today. We discussed another interaction parameters, scalar coupling. I discussed this varieties of features of scalar coupling. First of all, it is a scalar coupling is a covalent bond mediated coupling where the polarization transfer between 2 spins takes place through covalent bond. How it occurs we can explain through Dirac model, but I am not going into the details because in one of the earlier courses we have discussed this at stretch. But salient feature you should know, it is a scalar couple, covalent bond mediated scalar coupling. It is just a number, it is called a scalar quantity. It does not get average out like internuclear vector, it does not depend upon internuclear vector. And one proton can couple to any other number, any number of homo and heteronuclear couplings of different strength. It could be homonuclear and heteronuclear. When one proton is coupled to other proton, it become a give rise to multiplicity, become doublet, doublet of doublet, doublet of doublet of doublet, like that. 1 become 2, 2 become 4, 4 become 8 lines, like a family tree approach, it keeps undergoing splitting. So all these things we discuss at stretch. And I took the simple example of 2 protons coupled, A and X. A will see X, this is A proton, it will see X in 2 orientations, X alpha and beta. Because of 2 energy states, it will become a doublet. This X will see A in 2 orientations, alpha and beta, this will become a doublet. And doublet 2 peaks move equally away from the center of the chemical shift. That is what I showed. If this is the chemical shift, it will move equidistance on left, one peak, move equidistance on other side, right side from the center, and the separation becomes J. If you measure the separation, that means from the center it moves by J by 2 and from the moves to the left by J by 2 and the total coupling is J. Similarly for A other spin, if it is A moves J by 2 to the right, move one peak moves J by 2 to the left, the coupling separation between these two is JAX. This is simply for 2 spins. We can understand this for more spins later. So I am going to stop here. We introduced quite a bit about the coupling, lot more to understand about the multiplicity, how it comes about scalar couplings, which we will discuss in the next class. Thank you.